Ladies and gentlemen, Vice Provost Postvet, Associate VP Research Amsden, Dean Lemieux, good afternoon, everyone. My name is Amir Fam. I'm a professor of civil engineering and Vice Dean of Research in Smith Engineering here at Queen's. I'm also a fellow and have previously been a member of the College of the Royal Society of Canada. I must say, though, that I am the most junior fellow among the distinguished speakers and honorable guests, barely a 1-month-old fellow. On behalf of myself and Professor Emeritus John Burge, from the then School of Drama and Music at Queen's, and also a fellow of the Royal Society of Canada, we would like to welcome you all to this exciting afternoon. John sends his regrets as he had to be out of town for family reasons, but I must say, John did more than his share of the heavy lifting that goes behind the scenes for these kind of events. I am very grateful to have with me today my co-moderator, Professor Craig Walker, professor of drama, also from the Dan School of Drama and Music, and a fellow of the Royal Society of Canada, who has very kindly and graciously agreed to fill in for John. John and I have been the co-chairs of the Royal Society of Canada Eastern Ontario Symposium, previously known as the Eastern Ontario Seminar, for about 8 years. This event has a very long history at Queen's and used to take place back then in the University Club. This is the second consecutive year the event is being held at this beautiful venue with all the state-of-the-art technology it offers. The event this afternoon is being live streamed, so I also wish to welcome our viewers online. Our world is really changing at an unprecedented pace. Climate change, environmental degradation, growing mountains of waste, and global health challenges. They all remind us daily of the urgency we face nowadays. These issues go beyond borders and disciplines, demanding innovative thinking and collaborative efforts and solutions. The research you will hear about today speaks directly to these challenges and also offers new approaches that align with the United Nations Sustainable Development Goals. Together, these contributions highlight the vital role of science in shaping a more resilient and more sustainable future for our world. There will be 4 presentations on diverse topics today. Each talk will be about 25 minutes, followed by a short period of questions. There will be a 20 minutes intermission with bar service and food between the second and third talk. Finally, I wish to extend our sincere gratitude to the Royal Society of Canada, the Office of the Vice Principal Research, and the Isabel Bader Centre for the Performing Arts, along with its wonderful staff, for sponsoring and supporting this event in a variety of ways. Thank you. I also wish to thank our distinguished speakers, who are all affiliated with the Royal Society of Canada, for accepting our invitations. With this, I wish to proceed with introducing our first speaker. Richard Bathurst is a Professor Emeritus of Civil Engineering at the Royal Military College of Canada, where he has taught since 1980 and holds a cross-appointment with the Civil Engineering Department at Queen's. A Fellow of the Royal Society, he is recognized as an international leader in the application of high-performance plastics, otherwise known as geosynthetics, in civil and has civil engineering, earthworks construction, and his work has informed modern construction codes both in Canada and the US. He has published more than 230 journal papers and travels widely to deliver keynote lectures and short courses, and is the editor-in-chief of 2 highly acclaimed international journals. Amongst many other recognitions, he was awarded the 2024 Julian C. Smith Medal of the Engineering Institute of Canada for achievements in the development of Canada. The Bathurst Lecture was recently established by the International Geosynthetics Society in recognition of his contributions to soil reinforcement technologies. today, Richard is going to talk to us about finally a good news story for plastics, modern geosynthetics in geotechnical applications. Please join me in welcoming Dr. Bathurst.
Thank you, Amir. Thank you, the Royal Society of Canada, Eastern Ontario Symposium, for giving me this opportunity. The topic of my presentation has been introduced. Finally, a good news story for plastics, because I'm sure all of us are familiar with the bad news stories. So here is finally a good news story. Geosynthetics. What are geosynthetics? Geosynthetics are specifically manufactured to be used in civil engineering, geotechnical, and geoenvironmental applications. And there are certainly today a large number of these types of products. Nothing's happening. I'll reach out to the technicians and say, help. It was working. I think I know what the problem is. I think I have to restart my talk here. Not sure how long I was going for. I don't know, that might be it. I think it's on now. Excellent. There we go. So, what are geosynthetics? Geosynthetics are synthetic polymer materials that are specifically manufactured to be used in civil engineering, geotechnical, and geoenvironmental applications. And as I said, there are many types of these products, including those classified as geogrids and geotextiles. And the geogrids are the grid-like materials that you see in this slide. And here you can see the sheet-like materials, which are geotextiles. And I have some with me in case some of you would like to touch these materials. Other types of geosynthetics include plastic sheets, which we call geomembranes. And these are used as components to form a barrier or liner system at the bottom of landfills, for example. And the world expert is here, Kerry Rowe, who has spoken on this topic many times. And I'm certainly not going to crowd his space. These liner systems are often made up of multiple types of geosynthetics, as you can see here. Other applications include the placement of geotextile sheets below fill layers in order to reinforce and stabilize road beds. And it's another example of a modern technology which unfortunately is buried, so most lay people don't know that it's there and it's operating in our favor. Here's another example. To a lay person, this tiered concrete wall appears to be a simple gravity-type structure. But the magic is behind the facing units, there are these layers of high-performance plastic material, in this case geogrids, and these materials are adding strength and stiffness to the fill material behind the facing. This slide that you see here shows some of the construction steps in building such a wall. So here are the facing panels. Here are the geogrid layers which are attached to the facing panels. They're being pre-tensioned. Then they get buried with the backfill soil. And this process is continued up the back of the wall. And my focus is on the use of reinforcement geosynthetics in earth retaining wall applications. And this is something that has consumed my professional and academic career for about 4 decades. But it's sort of fun to recognize that it's not unusual that technologies that are common today in civil engineering earthworks have antecedents from the past. So here we have a slide of a ziggurat. This is a type of ancient. The remains of such a structure can be seen. And here we're seeing remnants of a ziggurat. It's about 70 meters in height. But if you focus your eyes, you'll see what appears to be layers or stratigraphy. And on closer inspection, what we find are layers of reed mats. So the ancients understood that they could build these structures higher and make them more stable by including, layers of reed mats to strengthen the soil. The concept can be understood by this simple analog that I show here. If we were to place, granular soil like sand, it would stand at its natural angle of repose or its internal friction angle. In order to make it stand at a vertical or near vertical change of grade, we could introduce layers of paper. And here, these balls are an analog for this granular soil. Now, we don't use paper. We now use high-performance reinforcement geosynthetic products. These include woven geotextiles. So they look like textiles, but they're specially manufactured to be strong and durable in this environment where they're embedded in soil to improve the soil properties. An alternative are what we call geogrids. And these look like crudely chicken wire, if you like, and they're made from different types of polymer materials, including high-density polyethylene or polypropylene or coated PET type. And quite frankly, this was a revolution in geotechnical engineering. And I'm lucky because I was at a point in place in time when these materials were essentially invented. And I spent a career trying to figure out how to use them or how they work. And these, again, are not the plastics that we might be familiar with in a social setting, everyday setting. These are specially manufactured to have high strength and stiffness. And here, for example, you can see a relatively small specimen of this geogrid type material. And hanging quite comfortably from this material is about a ton of load. And the material still remains its strength and has low deformation. The first geosynthetic reinforced soil walls were essentially wrapped face type. So what happened was sheets of geotextile were placed in horizontal layers. They were buried in the backfill soil and then brought around the face of the wall in order to keep the soil from spilling out. And the result was this composite block of soil and geotextile. Here is the first wall of this type, which was constructed in the state. 1974, I might add, it's still there 50 years later, and it was actually, samples were exhumed from this wall not long ago, and the material was still intact and performing its intended function. It was a wall that was used to support the side of a road embankment over a gully or swale. Larger structures were constructed later. This is a wrap face wall again. Look at the cross section. And this structure was the highest structure of its type at the time. And we learned a lot from this wall because it was instrumented. Here is another type of geosynthetic reinforced wall, and there are many different types. This has sort of like a gabion face. So the facing is made up of wire and stone, but the reinforcing function, again, is being carried out by these horizontal layers of, in this case, geogrid reinforcement. So here, again, is another shot, full-height concrete panel facing. Here, the reinforcement layers attached to the facing and strengthening and stiffening the backfill. So, what is the motivation? Well, the motivation for the use of these mechanically stabilized earth walls, if you like, is cost savings. And the technology was driven by practical engineers in the field that actually got ahead of the technology and the understanding of how they worked. So it was driven by business. We're going to make some money. And this slide here demonstrates what I mean by cost savings. A survey was taken of U.S. Department of Transportation engineers who were specifying these types of walls. And the first thing they were asked was, how much does it cost for a wall on a meter face basis, all in? And they supplied for conventional gravity walls this curve that shows the unit facing cost of a wall with height. And then they asked the same departments of transportation, well, what is the cost of these geosynthetic reinforced soil walls that are performing the same retaining wall function? And you can see quite clearly here that these solutions were quite cost effective. And as a rule of thumb, about 50% cheaper. So this was a huge incentive for the use of these walls, or this technology. But the question still remained, still very late in the use of this technology, was how do they work mechanically, and how do you design for them? And this question formed part of a symposium that was held at the Royal Military College in 1987 and funded through a NATO scientific grant. And this allowed us to bring together world experts. And as part of that exercise, we had a prediction symposium in which we built 2 full-scale walls in the lab at RMC and asked these experts to predict the performance of these walls, like how much strain in the reinforcement, how much would the walls move. And they looked around for the youngest, previously minted PhD grad, which was me, and said, okay, you go build those walls. And that's how I got started. Carrie's in this slide here, for those who know Carrie. And we built 2 walls. You can see them here in photographs and in the cross sections. The details of the walls are really not important to this discussion. But the outcome from this exercise was that the predicted reinforcement strains and wall deformations varied widely between predictors and were generally inaccurate. So we clearly didn't understand how these systems worked mechanically. So we started again, and we took two paths of research. The first is we collected data from full-scale instrumented field walls from around the world, and we simultaneously carried out a parallel investigation, building and testing carefully instrumented full-scale walls in the RMC retaining wall test facility. So here is some photographs of an actual full-scale field wall that was instrumented. And you can see this wall is about 6 meters in height, and you can see the reinforcement, and there's instrumentation here. And this was just one of several hundred of these type of walls that we collected over many years. Meanwhile, back at RMC, with a new, larger retaining wall test facility, we built a series of these reinforced retaining wall systems. And here you can see the facing of such a wall. And basically, they're just two giant bookends in which we could build walls that occupied about 70 cubic meters of soil. And this project, interestingly enough, the major funding came from 12 U.S. state departments of transportation. It lasted for about 11 years. So this was a real coup for us because this was the only facility of its type in North America where this type of testing could be carried out. This slide here shows one of these walls under construction. It's about half built. You can see the test facility sidewalls. This is the wall facing, and you can see the reinforcement in place and various instrumentation. In cross-section, this is what one of these walls would have looked like. And you can see the labeling here. There's strain gauges and other types of measurement devices. In fact, in a typical wall, there was more than 300 pieces of instrumentation. So we measured everything. And after these walls were built, we surcharged them. We placed airbags on the top of the wall that we could inflate. And we could inflate them to quite high pressures. And in fact, we could fail the walls. This is fun for civil engineers. And after the tests had failed, we would go in and excavate from the top to the bottom of the wall to see what happened visually, to see where the deformations were happening internally within that reinforced soil wall. And we did that for 11 structures. Now, using the data, both from our field walls and from our full-scale laboratory walls, we were able to compare the measured strains in the reinforcement to predicted values using different models. And this is important because this is the big key question, is how much load goes into those reinforcement layers, because those reinforcement layers are what are holding this soil mass together. And having all of these measurements, we were able to plot the measured loads in the reinforcement against predicted loads. Now, if it was a perfect model, all of these data points would fall on this one-to-one correspondence line, which is clearly not the case here. So this old model, which was called the simplified method in those days, was a poor predictor, a poor performer. These measurements and our better understanding of how these systems worked allowed us to come up with a new model, which is called the stiffness method. And with this method, we got a much better correspondence between measured and predicted. You can see it visually. I could prove it to you statistically. So a practical result of this research was a new design method. Now, in North America, if you're in the business of designing reinforced earth structures, there are two codes. There's an American code, and there's a Canadian code. And these, depending on your jurisdiction, you'll have these volumes in your bookcase. And they're codes. You have to make sure that you design to satisfy these codes. And a major contribution of our work was that the stiffness method is now in both codes. And this is, as I say in this slide, this is a paradigm shift. It was a completely new way of thinking about how these walls behaved, recognizing that it was the stiffness of the reinforcement which was a major player in developing the loads in these reinforced soil masses, and not the strength of the soil, which was how people thought prior to our work. And the the outcome from this method was that using the stiffness method, the predicted loads in the reinforcement are more accurate. You didn't have to use as much reinforcement. And where you place the reinforcement layers in that reinforced soil mass was more effective. And at the same time, if you use this method, you are guaranteed a minimum level of safety for these structures. But that's not all the good news. Okay? The other good news is related to sustainability. And this is a word that is used quite frequently these days. And when we talk about sustainability, broadly defined, so sustainability is based on 3 pillars or concepts. One is environmental impact, cost, and what we call societal or functional criteria. We want to keep the environmental impact of our structure to a minimum. And environmental impact can start right when you start digging materials out of the ground, when you start transporting the materials, when you place them. Of course, you want to be cost effective. We've already spoken to that. And also you want systems that have some flexibility when you design them. You know, they aesthetically they look okay, these type of things. And so there are methods now to quantify the sustainability of engineered structures. They can be buildings or they can be retaining walls, in order to give them a score, with a high score, with a higher score meaning a structure which is more sustainable. So what we did is we looked at 3 types of retaining wall systems. Gravity structures, which have been around for a long time. T or L-shaped systems. And then finally, these MSC wall systems, these polymeric reinforced wall systems. All of them are performing the same function. That is to maintain a vertical change of grade and to support soil behind a facing. And the outcomes were quite interesting. So again, in the sustainability assessment, we are looking at environmental impact, we're looking at cost, economic, and societal and functional. And if we look at the top graph, and here you can see the vertical axis has the sustainability score. Big number better, small number worse. And let's go over to a really high wall, like 15 meters. Here you can see that the retaining walls with the polymeric reinforcement, and to a lesser extent steel, have much better sustainability than the conventional solutions that have been used prior to the invention of these geosynthetic reinforced soil walls. On the bottom plot, the nice thing about this scoring system is that you can put different weights on the environmental impact, the economic impact, and the societal impact. So if you personally or the jurisdiction that you're trying to sell these systems into is more concerned about environmental impact, then you can weight your scoring system in favor of environmental. And if you do that, you'll find that the difference between the polymeric solutions and the conventional solutions is even greater. And what we're finding today is that in many jurisdictions, you have to supply the owner or perhaps government agency that's reviewing your designs, you have to supply this type of assessment as part of your bid for projects. This is what's happening as we move to a greener world. And so these geosynthetic solutions help us in moving in that direction. So, the good news. So in summary, there is some good news. Reinforced soil walls constructed with relatively extensible, polymeric reinforcement materials are now a mature and proven technology. This is a relatively new technology in civil engineering and in earthworks engineering. And they allow civil engineers to construct cost-effective, durable, and sustainable retaining walls. I'd like to, of course, conclude my talk by giving a shout out to all the people that have helped me over this long journey. You may be interested that each one of those full-scale walls that I showed you pictures of, they took anywhere from 6 months to a year to build. But fortunately, a tremendous benefit of being at the Royal Military College of Canada was that I had a stream of master's students, all of whom were serving officers in the Canadian Armed Forces. And you just had to wind those guys up, and they would plan this whole operation. And so they were just ideal candidates for carrying out this repetitive construction of these different retaining walls. But there are also, postdoctoral students and PhD students that helped over the years. And I had two people that were very useful. One of them was this fellow at the top here, Tony Allen. He was until recently, he was the chair of the technical committee that wrote the code, the American code for earth retaining structures. And so he was on the front lines, and he was the guy that used to call me up and say, we got a problem, we need a solution, you're an academic, this seems like good work for you. And this partnership has lasted for 35 years. And then I had other friends. For example, I have a doppelganger, if you like, in Japan, who has the same job at the National Defense Academy in Japan that I have or had at RMC. And he happened to be interested in the same projects or the same technology. And so he was able to gather experience and data from Japan. And that was also incorporated in our new stiffness method, so that the method is not only applicable to North America, that is Canada and United States, but also internationally, and is gaining favor in other countries like Japan. So I thank you for your time. And Amir, I don't know if there's time for questions.
Let's thank Professor Bader.
Thanks.
Great talk. Thank you very much. So we do have time for questions.
What is the plastics used for the sheets? What's the lifetime?
Well, that is an excellent question. We all complain about plastics because they never decay. Right? So they're very durable. We have done the design life for these structures typically is like 75 to 120 years. When we test these materials using advanced temperature time superposition, their lifetimes can go out to thousands of years. So durability has not been a problem as long as when you build them, you don't damage them. But each of these codes that I spoke about has specific guidelines about what type of soil you can use in the backfill and how to place it so it doesn't damage the reinforcement during construction. So its lifetime durability is not a problem.
I'm just wondering whether you have any local examples that we could go and take a look at.
Yes.
Maybe, kick around a bit.
I have them in my bag.
Well, no, I mean...
Sorry.
In the field, are there any examples of these walls in the field in Kingston?
Well, the problem
locally?
is they're ubiquitous. It's just you don't notice them.
I see.
It's a shame, you know, you've probably driven past them so many times and you can't appreciate, you know, the engineering that has gone into them. And the thing is, when you do see it, it just looks like a conventional concrete-faced wall. But there's magic happening behind.
So could I just ask you, the mention of Japan just made me wonder how they, these retaining walls manage during an earthquake. Are they better than the conventional?
Yeah, that's a wonderful question. And, you know, many of the talks that I give to people that are in the business are focused on this very issue. And generally speaking, these walls tend to be more durable in earthquake because they're a little bit more flexible. So they can sort of move with the ground shaking. And I have slides where we have a conventional wall, showing the conventional wall after an earthquake, and then just down the road, one of these geosynthetic walls, same earthquake, and it's still standing. So that's one of the additional benefits of these types of systems. They're more flexible.
Okay, here is a civil engineer asking a civil engineer.
No.
In the large-scale experiment you did in the lab, I saw that there is two guiding walls or two temporarily retaining walls, and then you built the layers in between.
Yes.
Were those removed after?
No.
So how much load is shedding to those walls?
Oh, this is a real civil engineering question. It's no fair. You should be restricted. So your question is, you can see that we built these walls inside like a silo. And this very astute question is asking, well, will those sidewalls help to prevent the wall from moving out and for developing strains in the reinforcement? And that mechanism was anticipated by lubricating those sidewalls. And there's a little bit of a hint of here. You can see that we use multiple layers of plastic sheeting. Actually, they were vapor barrier, this type of vapor barrier that you use in your house. And then between the layers, we put like a super grease. Okay, so any movement outward would not be restricted by the sidewalls.
Thank you. And yes, one more there.
Thank you so much for the presentation. I just have a quick question regarding the rubber. Have they considered
I didn't get the first part.
Any research or consideration has been given to use rubber instead of like plastics, like like a tire in the machine, the rubber tire of the machine. They have rubbers. You know what I mean?
Not for the layered reinforcement because it's not stiff enough. The material has to have enough stiffness, if you like, to grab the soil and to carry load.
Any final questions? Please join me to thank one more time Professor Bathurst. Thank you very much, Richard.
Thank you. So I'll unplug this.
All right. We now move to our second speaker, Professor Kathy CRUDDEN is the Ali V. Douglas Distinguished Research Professor at Queen's and Queen's National Scholar and a Tier 1 Canada Research Chair in Metal Organic Chemistry here at Queen's. Kathy is the Scientific Director of the Carbon to Metal Coating Institute, a cross-disciplinary multi-million-dollar collaboration spanning microelectronics, corrosion, and cancer therapeutic research. She holds a cross-appointment at the Institute of Transformative Biomolecules in Nagoya, Japan. She has won numerous research awards, including the Clara Benson Award, Fellowship in the Chemical Institute of Canada, a Calum Research Fellowship, the R.U. Lemieux Award, Montreal Medal, and an Arthur C. Cope Scholarship. She's a fellow of the American Chemical Society and was elected to the Royal Society of Canada as a fellow and also fellow of the Royal Society of Chemistry in the UK. In 23, she received the NSERC Polanyi Award and is an elected member of the American Academy of the Advancement of Science. Kathy was the president of the Canadian Society of Chemistry in 2012-13. She is currently the editor-in-chief of ACS Catalysis and sits on the editorial advisory board of many high-impact journals. She founded the NSERC Chemistry Liaison Committee and is frequently asked to participate on national and international review panels and evaluation committees. Her recent work identifying a new class of carbon-based SAMs has been called a game changer and the new gold standard by international experts. Kathy will talk to us today about the power of organometallics, from catalyst to self-assembled monolayers to atomically precise nanoclusters. Please join me in welcoming Kathy CRUDDEN.
Thank you very much, Amir. I will try not to let you down after that very generous introduction. Thank you all for coming. I understand people are missing the Queen's Waterloo football game and also the climate march, and it's a beautiful day, so I will try to make this worth your while. So the research that we're going to talk about today is very chemistry-centric, but I know I have a very diverse audience, so we'll try to make sure this is interesting to everybody. So let's start with this statement. Metals are inherently unstable, right? That should scare everybody because we're all in a building that's made of steel girders. What's keeping your seats on the concrete is steel connections. But this is completely true because if, let's see here, okay. I'm not going to be able to walk around as much as I usually do. Oh, there we go. If we think about how we make steel, right, what do? We take iron ore out of the ground, right, and we smelt it in a process that is incredibly energy intensive, right? So if you have to put energy in, what you're making is something that's less stable, right? The main form of iron that it's happy in is iron oxide, otherwise known as rust. So we can prevent this, but you can never stop it, right? I think Einstein said the only physical law that would never be overturned is that of thermodynamics, right? So what we want to do is keep things in service as long as possible. And how do we do that? We typically do this with coatings and with paints, but this doesn't always work very well. So if we look at the costs of corrosion, we can see that over 3% of a country's GDP is spent on corrosion prevention, maintaining structures. In Canada, that's $66 billion, right? I don't know about you, but I would rather we put that money into hospitals or doctors or education or something like that, right? It's predicted that a quarter of this cost could be saved if we did a better job of protecting metal surfaces. Let's look at increasingly smaller structures. What about on the micro scale? So semiconductor interconnects are becoming smaller and smaller, and it's really challenging how these are made. So everybody in this audience, except maybe the 3-year-old, has a cell phone, right? In that cell phone, there are 20 linear miles of copper. So all of that copper, and I'm saying miles because this was told to me by an American, all of that copper needs to be protected and frankly needs to be removed because copper is not going to be the best metal. But we need to think about how to make these structures smaller and smaller. And do we think this is important? Absolutely. So I love this quote, semiconductor chips are the new oil. What does this mean? It means that the countries that control production of semiconductors control the world. We all remember during the pandemic, you couldn't make a toaster without a semiconductor chip, right? And so manufacturing is controlled by those people who make the microelectronics chips. All right, let's go one layer down now, nano. nanomedicine has something that has attracted the attention of the world for decades, but it has really failed to live up to its success in the lab. There are multiple problems. I'm not going to go through all of them, but we are going to try to address these. So how are we going to try to address these problems? Who are the rock stars that are going to solve these problems? The answer is molecules, right? When you're talking to a chemist, molecules are always the answer to everything. So what is a molecule, right? A molecule is a group of one or more atoms that are put together in a specific way. So one of my friends said that this is like the atoms are the alphabet and the molecules are the words. So we take the atoms and we put them together and we make something that has meaning, that has function. And it actually matters a lot how we put these together. So let's look at one of my favorite molecules, ethanol. Right? I think this has been changing the world for better and for worse for thousands of years. This is a very simple molecule, right? If we break this down a little bit, this is C2H6 oxygen, right? It actually has a pretty high boiling point for something that is that small. But interestingly, if we compare this molecule, this is also C2H6 oxygen, but we've moved things around, right? So we've taken this carbon and we've put it on the other side of that oxygen. So here we have an oxygen-hydrogen bond, and here we have two oxygen-carbon bonds. I will also tell you, chemists draw these lines. Those mean the covalent bonds that make up everything. They're the strongest bonds that we know of. And actually, the CH bonds are really strong too. They contain a lot of energy, which is why we burn them in terms of hydrocarbons. They possess a lot of energy. This is dimethyl ether, and it has a boiling point of minus 24 degrees Celsius. It's a gas at room temperature. So that shows you that how you put words together, how you put the alphabet of molecules together makes a big difference in terms of their properties. What about some other molecules? Penicillin. Clearly, this is a much more complicated molecule, but I'd say it's one of the molecules that's changed the world. This is one of the few things, antibiotics are one of the few treatments that's actually curative, right? I don't even know how many lives have been saved by this molecule. And here's an incredibly simple molecule that has also changed the planet. This is ammonia. 1 nitrogen, 3 hydrogens. If we did not have this molecule, we could not feed the world because this is the #1 constituent of fertilizers. So molecules' structure and function is really a lot of what chemists spend their time thinking about. Let's talk about size. So what is nano? This is fullerene, really interesting molecule, won the Nobel Prize. It's a series of carbon atoms put together in the shape of a soccer ball, and it's about 1/1000th of a meter in diameter. Let's compare that with a few things that are more simple for us to understand. So soccer ball and the Earth. So the size of a soccer ball compared to the size of fullerene, this is about 100 million times smaller or larger, depending how you look at it. And if we compare the Earth to a soccer ball, that's also 100 million times. So when you think about a molecule, the relationship between a molecule and a soccer ball is the same as a soccer ball to the entire Earth. That shows you the kind of scales we're looking at. All right, so let's get into my research a little bit. Another technical term is a ligand. And in my world, a ligand is a molecule that binds to a metal. And so we're very interested in how ligands bind to metals because they change their properties a lot. Turns out carbon monoxide, although this is a very dangerous molecule, very small molecule, is a phenomenal ligand for metals. And I take this out just to show you the kind of impact we can talk about. So carbon monoxide is a gas, right? And it's handled in cylinders like this. I spent my entire PhD as a wrenching, cylinders and cylinder heads off and on. And one other person way before me who did this actually noticed an orange liquid dripping out of this steel regulator. And what is that liquid? Turns out that's iron pentacarbonyl. So this is a single iron atom with 5 carbon monoxide molecules around it. And the carbon monoxide changed the properties of the metal so much that it went from a very hard, very tough material to a liquid with the boiling point of water. So that shows you how much ligands can have an effect on metals. In nickel, this is even more crazy. Nickel tetracarbonyl has a boiling point that's almost that of diethyl ether. And that actually turns out to be rather dangerous, because you don't want to be inhaling anything that has nickel that will then plate out onto your lungs. So nickel pentacarbonyl is rather dangerous. Okay, so the molecule that we are interested in is this particular molecule called we'll just call it an NHC. It's very much like carbon monoxide. It has a key carbon bond to 2 nitrogen atoms, and it binds really strongly to metals. And in ancient times, and by that I mean the 1990s, these were used first to make bonds to metals to develop catalysts, which is an area of my expertise. And so we had studied these since I was an assistant professor, and it was only about 12 years ago that I asked the question, what about a metal surface? What if we considered a metal surface to be a collection of atoms? If that's the case, these ligands should be outstanding for binding to metal surfaces. And it turns out they were. And the world got very excited about this, actually, because up until this time, we had not had very good strategies to put organic molecules onto metal surfaces. I'll show you a little video that was made. Metals themselves, especially the atoms on the top, are very unstable. They don't like to be not within the bulk. And when you put these carbines on their surface, you can make them relaxed and make them less energetic. And that's important for a lot of things. So this was the main discovery that prompted myself and a few other people in the depths of the pandemic to apply for this grant, the Transformative Research Grant, $24 million, and to try to take this concept of this carbon-metal bond into macro space. Could we protect steel? Could we protect things in aerospace? Could we protect cars, wind turbines, bridges? Could we work in the micro space and control how we're generating and forming semiconductors? And could we affect nanomedicine? Right? And it started with these 3 people and myself. Gong Zheng from University Health Network, I didn't even meet him until after we had the grant. So we did everything online preparing for this grant. And with the help of some phenomenal young faculty members and an amazing staff, we put together this Carbon to Metal Coating Institute that's been running since that time. So we'll start at macro. I will say this was the highest risk for us because we had actually not demonstrated that this worked on steel. We'd only been working on pure metals. But we felt like this was a big potential win because if you look at things like pipelines, bridges, wind turbines, ships, the way these are protected is really using physical coatings, paints that can delaminate. And our idea was we could make a covalent, a chemical bond here, and maybe even to the epoxy coating to protect pipelines and particularly things like offshore wind turbines, because these are very sensitive to corrosion where the splash zone happens, so where the sea hits the metal. We actually have a partnership now with Ocean Networks Canada, and they've taken some of our coated metal surfaces, they put them at the bottom of the ocean, and they're going to pull them up after a few months, after a year, and see how they survive. So that's both exciting and terrifying. We do know that they work well. Sorry. Okay. We do know that they work well. So you can see that uncoated versus coated, you can see corrosion happening on the uncoated. We've now compared this coating to commercial coatings, and it exceeds what's known in the industry. So that's been very exciting. And we've now partnered with ArcelorMittal, which is the world's leading steel and mining company, to try to look at this in an automotive sense. We have a phenomenal postdoc in the audience, Dr. Monica Snowden, who's made these into polymeric coatings. So you now have multiple points of contact, and you can spray these. So we're looking at how we can spray them in outdoor settings. We're also looking, thank you, we're also looking at spraying the actual metals. So in high velocity air fuel sprays, you use things like copper particles and spray onto metals to protect them. And what happens is that you get this actually called a splat boundary. So the metals fly towards a damaged metal structure, and they splat and make new metal. Now, if they oxidize en route, then you don't get good adhesion. So we have coated copper particles in this really interesting resonant acoustic mixer, which uses no solvent, and then sprayed the metal coating, and it works extremely well. Survives a lot better than without the protective coating. So now going back to, again, we're going to go smaller and smaller. Semiconductor chip manufacturing, as we want more and more performance out of smaller and smaller chips, we have to think about how we create these fine metal lines that connect and make signal. And what's normally done is you have an existing, an existing pattern. Let's say this is, the blue is a metal, and in between is insulating. So you're insulating the lines until you want them to touch. And then when you build your chip up in 3D, what you do is you put down a coating of metal, probably copper, you mask it, and then you take off. So it's subtractive processing. That is actually very dirty. I'll talk to you about that. But if your mask misaligns, you have really big problems. You get what's called an edge placement error. And now if we're talking nanometers, because new devices are nanometers apart, electrons can jump. And what does that give you? It gives you a short, and your device fails. But the idea behind putting all kinds of metal on and then taking it off and then cleaning is really dirty. So a large semiconductor fab uses 38 million liters of water per day. And that's the consumption of 300,000 people or 500 swimming pools worth of water. And I'm not talking lake water. This is ultra high purity water. And this subtractive manufacturing I talked about is responsible for almost half of that need for this ultra high purity water. So what are we going to do? Obviously, we're going back to molecules, right? So instead of a physical mask, what we're going to use is a chemical or a molecular mask. And so here we have a metal and then an insulator, a metal and insulator, and we want our carbene to bind, our ligand to bind to the metal. And we want it to protect that metal as we build up the insulator, and then we take it off. So this is very similar to what every one of us does when we paint, right? Nobody trusts their hand when they're painting. You put on a strip of tape, and then that allows you to protect this surface. So our carbenes are a molecular strip that's going to protect the metal while we build up what's next to it. So let's show you how this is working. Here we're using cobalt. Cobalt is a metal that's of big interest to replace copper. And you see you have here cobalt, and then this is insulator, cobalt insulator. And when we deposit our molecules, they go specifically with high selectivity onto the metal. They don't go on the semiconductor, on the insulator. And then when we deposit, increase the insulator here, you can see this is growing, and this is the metal protected by the carbene. Okay, there's a little splash right there, but by and large, this is working extremely well right now. And we're partnering with all kinds of semiconductor companies around the world to look at how this works. I do want to say we're very proud of the fact that we're trying to do life cycle analysis from day one. So we have a team member, Professor Annie Levasseur, who's an expert in the effect of chemical processes and humanity on the climate. We don't want to get in a situation where we develop something that's extremely good, never comes off, and then you've got a forever chemical, or you've got chromium, or something like that. So from the beginning, we're looking at this, and it seems right now to have toxicity that's equivalent to sodium bicarbonate, so baking soda. So far, we're very happy with that. Okay, nano. Anybody know where this is? Yeah, Sagrada Familia, right? I was lucky enough to visit there. It's fantastic. Nanoscience has been around for thousands of years, and actually early artisans took gold or silver metals and they mixed it with sand at very, very high temperatures, and that they found it glowed red or yellow. So all of the reds in all the churches in the world actually have gold nanoparticles in them. And it's a surface plasmon that gives that gold, gives the gold that red structure. Similarly, the yellow is all silver nanoparticles. Now, nobody knew that at the time, but I think it's really fascinating to see this mix between science and art. So what we're doing is trying to look at how nanomedicine can be improved. And this is really complicated, how one of the ways people are trying to use nanomedicine. So we start with gold nanoparticles. I'll come back to why gold. And what we need to do is we need to prevent them from corroding, essentially, in the body. Because what they do is a nanoparticle is not your thermodynamically stable state. Bulk gold is your stable state. And so it's going to try to get there, and we want to prevent that. And how do you do that? Molecules, right? So we protect the surface of the molecules, and in order to do that, you need a good organic to metal bond. And so people have been using sulfur, and it frankly has not worked well. And you need a tumor targeting ligand, you need a protective ligand, a photosensitizer, and if all that works well, what you can do is bind your nanoparticle to a tumor through the tumor targeting ligand, hit it with light or X-rays, and they generate reactive oxygen species, destroy the tumor, right? So that's a great idea, except that the metal ligand bond has not worked well until now. Okay? There's also another problem. Nanoparticles are an inherent mixture. This is a picture of nanoparticles we made in our lab, and you can see here that we're looking at them by the diameter, right? And there's a size distribution. They're not one thing, right? If you went to a pharmacist and you said, I want my medicine, and they said, okay, it's mostly this, there's a little bit of that, something else, you would not be very happy, right? So we want to solve that problem, and we've been able to make these things called nanoclusters, which are smaller. They have our carbene ligands on them, but this is now a single molecule. So we know every single element, and we know how many they are, and this is not a guess. And this is like now we know exactly what the word is that's been made up by all of those particular elements. Okay, let's take a step back and ask, why gold, right? Why would we use gold for this? So I hope everybody's familiar with the periodic table. The coloring might be a bit weird to you because this is the can I lick it periodic table. And the colors go, sure, go for it, maybe not the best idea, please don't, and see you on the other side. I mean, I would question this. Osmium, I would absolutely put there. So, but regardless, gold is definitely in the yes, you can lick it, right? So gold is a very stable, biocompatible element. And so with gold as the starting point, we've used our ligands, our carbon-based ligands, to make all kinds of different structures. I won't talk about how we can do that. We can talk afterwards if you want. Everything that we don't show is where there's a carbene. But you can see now all of these gold atoms are in different places, and they give different properties. Turns out that, like with everything, the simplest one is actually the best. And we've used this now with our collaborators to test in cancer cells. So these are KB cells, which is a type of cancer cell. And you can see that the nanoclusters get taken up because they turn red. Remember I said that the nanoparticles glow red. This is a little different reason, but they also are red. And what we've done is we've made clusters that have targeting agent on them through the carbene. And what we can do is we can see now they still get taken up. And if we add exogenous targeting agent, in this case, this is folic acid, something everybody knows. Many cells overexpress folic acid on their surfaces. And when we add extra folic acid, it kicks out the nanocluster. That's a good sign. That means that it's through that receptor that they're binding. Working with Chantal Capocotti, who's a rising star in chemistry, we've put on sugars. Many cancer cells overexpress sugar because they're growing, so they have sugar receptors, and we can also then target that way. Also, we've been able to now show that when we hit these cells that have our nanocluster in with light, we get a cell destruction, so up to over 90% destruction of the cancer cells. So that's really exciting for us. And just to give you an in vivo example, this is a mouse that our friends in UHN have implanted with a xenografted tumor here. And what they've done is, you can see that the tumor is treated with radiation, which is what we would normally do for cancers. 50% of people with cancer are treated with radiation therapy. And what we can see here, the control, the mice did not last more than 24 days. When we treated with our cluster, there was really no change. Radiation, in this particular case, did not help. But when you combined the cluster plus radiation, you see a huge change. So this is really positive. We have a long way to go, but it's really extremely encouraging results. So the United Nations Sustainable Development Goals are really important. Our work hits at least 4 of these, and this is really important for us at this stage in our careers to be able to contribute. I will say the Institute also cares a lot about the people that we have. All G20 countries have identified skills development as a strategic objective. And 2 of the really fun things that we do at the Institute are we give students sabbaticals. I mean, a PhD is a long time, right? So halfway through, students get funded to go to a different country, often Japan, where I have a satellite lab, but Sweden, Switzerland, Finland, wherever they will learn what they need to learn. And we also give seed awards to ideas from students. So they get $20,000 to take and hire students. They have to do the hiring, they have to do the interviewing, and then they're responsible for the student for the summer. So it's really a fun thing to do. I do want to thank our incredible staff. Staff often don't get the thanks that they need. Without the people on this slide and many others, it would be impossible to do the work we're doing. So I really hope that we continue to support and fund staff at our universities. And of course, my students and postdocs. They're so creative, dedicated, hardworking group. And it's a delight going into the lab to be able to work with them. Thank you also to Queen's. Queen's has been extremely supportive of me. When I was writing this grant and we were going through the different stages, every time I was asked, what do you need? The answer was always time, and everybody worked super hard to make that happen. So I really want to thank our dean, and I want to thank all the other university people, administrators who are here, who support research at the university. Thank you. I'd be happy to take any questions if you have them.
Thank you very much, Kathy. Truly inspiring. Lots of promise, lots of potential. We do have plenty of time, in fact. So, questions?
Is a mic coming?
Thank you so much. I have just a general question regarding the effectiveness of cathodic protection. They usually use it in the pipelines, you know.
Mm-hmm. Yeah, the cathodic protection is outstanding, right? So the real place that there are problems are, for example, in turbines on the splash zones. That and offshore wind is something that people are really interested in because you're not taking away arable land, you're not near people's houses, but they're so hard to repair. So cathodic protection is outstanding, but the splash zone is a real problem. Yeah.
Other questions?
So I apologize if this is terribly naive, but given the bonding qualities of the coating, do you have to customize instruments to apply it, or are existing instruments adequate?
Great question. I've heard someone say there are no stupid questions, only stupid answers. So hopefully I don't do that. But yes, in fact, when we first started this, a lot of the instruments are made out of steel, right? And so people were worried that when we put our molecule in, it would just coat everywhere. It turns out that that's not an issue. If there's ways around it, but yes, it's absolutely a concern. Yeah. What we've done when we do vapor phase depositions, we have the metal of interest that's in close proximity. But after a while, what you have to do with some of these instruments is you do have to do a bake out, because what we were finding was we would do an experiment with carbene 1 and then do an experiment with carbene 2, and all of a sudden carbene 1 is showing up because it was hanging around on the metal inside the tool. So we had to do a strong bake out in between. Great question.
Other questions? I actually do have one.
Yeah.
You cannot imagine how excited I am when I see a picture of a highway bridge or a pipeline or a wind turbine. I am sure my colleagues, Kerry, Rowe, and Richard, are also equally excited to see the potential for a future solution to our gigantic problem.
Yeah.
I remember giving Kathy a tour to my lab once, and I just remember the look on her eyes when she saw the scale we are working on. So a small sample in my lab is about a bridge, 15 meters by 4 meters. And I am privileged to be a member of your institute, Kathy. And the point I would like to make is the scaling up.
Yes.
Okay? People might not know that, but the infrastructure in Canada and other parts of the world is taxing your tax dollars beyond your imagination.
Yeah.
Arguably, it might be the second most expensive after healthcare, most likely. The scale of deteriorating infrastructure is enormous, whether underground or above ground, pipelines or bridges. So why? Big part of this is corrosion of steel.
Yeah.
Thousands, if not millions, of tons of steel are corroding right in front of our eyes every year. So this is a very promising solution. But when would you think we would be at a stage where you are able to scale up this magnificent technology to be able to use it on large-scale structures?
Yeah, that's a great question. I think we're finally ready to collaborate. We were not ready when we first talked, but I think we're finally ready. I think, Dr. Snowden's work on spray coating is really important. You're not going to dip a structure like that. You need to be able to spray. And we have a partner in the US who's ready and willing to go ton scale on the coatings whenever we have a good application. So
we are advancing into scaling up.
Yes, absolutely.
Amazing,
Yeah.
amazing. Other questions?
I was just wondering how bacteria like your coated surfaces, do you find that biofilms are repelled or encouraged?
Great question. I think this is right now the biggest issue we have. They do like it a little too much. So we need to make it a little less tasty. So that's fine. We feel like we're chemists, we can do that. But I agree, biofouling is a major thing that we're going to look at next, especially when we're going into the sea. But I think the fact that we can now make polymeric coatings is good, because there's a lot known about polymeric structures and how they resist or don't. So yeah, that's a great question.
Other questions?
Nigel.
I'm wondering whether this is just a surface coating or whether you can integrate it like a stainless steel so that when you get somewhere, it continues to.
Yeah, that's a great question. So whether this is like the chromium from stainless steel, whether it goes underneath or not. Right now, it's on the surface, although it depends on the metal. So it turns out that because the metal carbon bonds are so strong that in some metals, the coating can actually move the metals around on the surface, which can be very good if you want a structure that has metals where they shouldn't be and you come to an equilibrium on it. But right now it stays on the surface. It doesn't go underneath into the metal. Yeah, great question.
Final call for any questions for either speaker, Professor Bathurst or Professor CRUDDEN. Okay? Yeah. Oh, okay, go ahead.
Just a quick question. Have you heard about the idea of, I don't know, the eating gold powder as a medicine?
I think gold powder on its own probably doesn't do very much. You know, I think it's a very expensive treatment that probably does not much. Yeah.
But I heard some people are still talking about it.
Yeah, I mean, gold in the bulk stage, which powder is really bulk, is very inert. And that's why we use it for jewelry. So when I said metals are inherently unstable, I wasn't 100% truthful. Gold is stable. So actually gold and platinum a little less so, but that's the one metal that's very stable. But we're not going to build buildings out of gold, right? So because it's so stable, that means it's probably not doing anything, I would guess. Yeah. Yeah.
All right. Thank you very much. Please join me in thanking Professor CRUDDEN.
So welcome back, ladies and gentlemen. My name is Craig Walker, and I'm a Fellow of the Royal Society of Canada and a professor in the Dan School of Drama and Music here at Queen's University. And as Amir explained earlier, I'm pinch hitting for John Burge. John recently retired, and consequently he's busier than he's ever been in his entire career up till now. At any rate, I have the honor of introducing our third and fourth speakers. And first up is Amy LATIMER-CHEUNG, who is a professor in the School of Kinesiology and Health Studies at Queen's University. She's a member of the Royal Society of Canada's College of New Scholars. Amy is ranked internationally among the top 3% in research productivity and impact, according to AD Scientific Index. Over her career, Amy has published 270 peer-reviewed papers and has held millions of dollars in grant funding from all three major funding agencies in Canada, as well as at the NIH. Currently, she holds a $2.5 million SSHRC Partnership Grant, the largest funding opportunity available in the social sciences within Canada. Her research is at the forefront of creating and mobilizing research knowledge to promote quality physical activity experiences for persons with disabilities. Amy is the director and principal investigator leading the Canadian Disability Participation Project 2.0. CDPP 2.0 is a research partnership of more than 75 researchers and sport, exercise, and active play organizations working collaboratively to create quality experience in sport, exercise, and active play for children, youth, and adults experiencing disability. The practical research products she and her research team have developed have been translated into multiple languages for use worldwide and accessed in over 100 countries. In addition, Amy is the founding and current executive co-director of Kingston Rev'd Up, an exercise program for 200 adults experiencing disability. Amy is a long-standing member of the Participation Research Advisory Group that has a role in shaping Canadian physical activity agenda. And now, speaking on learning to prioritize quality over quantity, lessons from research partnerships, Amy LATIMER-CHEUNG.
Thank you. Excellent. Before I begin, I'd like to acknowledge the land in which we're gathering, and admittedly today they've given me far more than I've been able to provide. Certainly standing out in the lobby and overlooking the Lake Ontario and its waves and the sparkle has brought me calm as I've had the opportunity to speak amongst some of the greats. I feel nervous, but I'm really excited to share the work that I think is really, really important. It's hard to believe, but this photo was taken almost, well, to the day, 25 years ago. This was my first day of graduate school. And little did I know that this was the beginning of an incredible journey. I met with my graduate supervisor, Kathleen Martin-Guinness, that day. It was our first meeting in person. And Kathleen asked a broad question. She said, so, what type of research do you think you want to do? And naively I answered, I don't really know. I just really want to make a difference in the world. And that was the start of an amazing thing. Kathleen and I continued to collaborate and be long-term friends. In addition, I learned one of the most meaningful lessons as a graduate supervisor. Kathleen didn't scoff. Rather, she began to equip me with the skills to take on my quest. My research aims to promote quality physical activity participation for the 8 million Canadians experiencing disability in Canada. Imagine, or perhaps you don't need to imagine, bringing your child to a park and they have to sit on the sideline to engage with their friends because the playground is not accessible. Or arriving at the gym, hoping only to do a workout, but finding it's difficult to even get in to the facility. And once you enter, the members are staring at you because you're different. Or wanting nothing more than being on the field, but having to sit on the sideline to participate in sport. My research is aiming to transform physical activity experiences for persons with disability. In particular, we're striving to create quality physical activity experiences by training coaches, physical educators, and administrators to create quality experience. We're setting the standard for training qualified exercise professionals to promote and prescribe physical activity. And we quite literally are changing the landscape of playgrounds in Canada. To be successful in this work, it takes many, many, many people. And in particular, it takes the views and perspectives of persons with disability. Through this work, along with our partners, I'm on a long-term mission to create quality physical activity experiences. I am the director of the Canadian Disability Participation Project 2.0. This is, as Craig indicated, a research partnership in which I have the privilege of working with researchers from across Canada, as well as persons with lived experience of disability and community-based organizations that are serving and promoting sport, physical activity, and active play for our Canadians with disability. It's through these partnerships that I've been able to reach and work towards my quest of doing meaningful and impactful research. It's by asking questions that are important to these partners that I've been able to find and address that desire to make a difference. For the first 15 years of my research program, I aligned my research questions with the priorities of organizations that were striving to increase participation in physical activity. Take, for example, the Canadian Paralympic Committee, where there's pressure to perform, pressure to have as many athletes as possible, reaching and achieving gold medal status. So those are the types of research questions I began to answer. I began to ask, how do we motivate persons with disability to participate in physical activity? I also began to align my research program with the Public Health Agency of Canada, who had a particular initiative and interest in identifying and creating physical activity guidelines for Canadians. Unfortunately, these initiatives led by the Canadian government did not include persons with disability. We had no idea how much exercise a person with a spinal cord injury, for example, needed to do to achieve optimum health benefits. As a result, I had the opportunity to work with colleagues persons with spinal cord injury, and a number of organizations to create the first guidelines that are evidence-based to promote and include persons with spinal cord injury in physical activity. We further took this approach to explore and determine the optimal dose of physical activity for persons with multiple sclerosis, for example, as well as to review and understand the evidence about the optimal dose of physical activity for persons with Parkinson's disease. This is an area that continues to be of interest. We're advocating and challenging the World Health Organization, who recently released physical activity guidelines for persons with disability in the absence of using evidence from the disability population. While this work has been incredibly meaningful, and I do think it's had impact, certainly to know and be able to prescribe physical activity, we are hearing stories and realizing that there's got to be more. We continually hear stories of children showing up to physical education class and sitting on the bench or taking on roles as scorekeeper rather than being able to engage. We hear stories where children or adults would show up to participate in a swim program and be told, "I'm sorry, I just don't know how to help you." We began to explore what it truly means to participate. And in fact, the answer was right in front of us. The United Nations Convention of Rights for Persons with Disability suggests that participation includes both quantity of participations, that work I'd been doing early on in my career, the work that focused on how do we motivate, how do we get in the numbers, how do we get people showing up at the sports field, at the gym, at the playgrounds, but also how do we ensure that when someone engages in physical activity, they have a quality experience? And indeed, the UN Convention of Rights for Persons with Disability enshrines the right to full and effective participation in physical activity for persons with disability. And thus led the next phase of my research. And I must say it has been the most rewarding work that I've done so far. To do this work, we started at the fundamental question: what does it mean to have a quality physical activity experience? We drew upon the strategies and the approaches that we'd used to develop physical activity guidelines. These are the same approaches that are used and the rigor that is used to develop clinical practice guidelines, the guidelines that are used to determine optimal doses of hypertension medication, or the practices that should be used for screening, for example. This is a rigorous multi-step process. It involves partnership, understanding the questions that our partners might want to have addressed. Why is the concept of participation particularly important for some organizations? Then it involves conducting a series of systematic reviews and evaluating and examining the existing evidence. We drafted and began to create products or descriptions of what quality of participation might be. We also would identify gaps in this process and conduct our own research. We would explore and understand the experience of physical activity participation for persons with disability through qualitative and quantitative research studies. Through our work, we began to draft an understanding and a framework of quality participation. We sought out input from diverse user groups, including persons with disability, coaches, instructors, as well as caregivers. We further refined and drafted this framework, received additional feedback, and ultimately created the Quality Participation Framework that now serves and underpins our Canadian Disability Participation Project. From this work, we determined that quality participation is achieved when a person with a disability views their involvement in physical activity as a satisfying, enjoyable experience and the experience outcomes that they consider important. Now think about it. If you do engage in physical activity, have you had a quality experience? Maybe physical activity isn't your thing. Think of another recreational undertaking or another activity that you really enjoy. Think about it. What does it feel like? Who's present? Who creates this quality experience? These are the types of questions we've asked. And from this, we've determined that quality participation is a result of repeated and sustained quality experiences. So every time we have an athlete roll onto the field, we know that we need to create a positive and enjoyable experience. They need to experience these outcomes that are important to them. We further began to ask, what is it that creates these positive experiences? And we find that it is 6 fundamental building blocks. I'll explain them, and then I'd like you to think back to that experience that you thought of. Are there any building blocks that tie or explain your quality experience in physical activity? The first building block we find important is autonomy. We find that exercisers or children on a playground or an athlete has a more positive experience when they feel autonomous in their participation. And this is in the moment. So when they're on the playground, when they're at the gym, when they're out for their wheel. Autonomy has to do with the feeling of choice and independence. Next, we find that our participants find that feeling that they belong, feeling that they're part of a team, part of the group, perhaps part of the culture, is a critical component of experiencing quality. Next, feeling appropriately tested or challenged is a third building block. Engagement has to do with that feeling of being absorbed in the moment, surely like you're feeling right now. It's that time or that feeling when time just flies by. All of a sudden, that exercise session or that yoga session or that squash game is over, and it was wonderful. Next, we find that people experience quality when they experience mastery. This is when they achieve their goals, when they feel proud of what they've accomplished. And finally, when people can generate meaning from their behaviors. This may be social meaning or personal meaning. And it can be little things like, hey, we really need you on the field right now. Oh, I have a role. Or you're going to be team captain today. Or you're in charge of picking up the pylons. Small roles can make a big difference and make people feel like they belong and that they have a really positive experience. We further began to explore how do we create these building blocks. Again, through conversations, through observation, we've begun to identify strategies that coaches, physical educators, exercise professionals can use to create these building blocks on the playground, on the sports field, and in the gym. Having established what quality participation is and how we may create it, we also needed the critical piece to ensure that, yes, indeed, we have identified an important piece of the puzzle. Is quality participation actually important? And luckily, in fact, it is. Typically, we think of quality or quantity of physical activity being the primary determinant of well-being, both physical and psychological and social well-being. However, in our cohort of adults, of 400 adults with physical disability, we found that, in fact, quality participation is a stronger predictor of well-being than quantity of participation. So what we found is that quality physical activity participation may be more important for well-being than quantity of participation. And furthermore, we find that individuals who experience all 6 building blocks to the level that they desire are more likely to participate in physical activity. In recognizing how to create quality participation and recognizing its importance, our next strategy, our next area of research was to begin to explore what do practitioners need in order to create quality experiences. And this is really where our work is sitting now. We've created a number of resources that are available online and free for practitioners to use. I'm headed from here to a retreat with 100 volunteers from Special Olympics Ontario to share this work and to help them explore and think about how they're going to be using this and infusing this into their practice. We also are working with organizations that fund physical activity organizations, so they begin to move away from quantity and think about quality. They begin to move away from thinking that they need to have 100 people show up to their have-a-go days or their try-it days, and realize that, you know, if you have 10 people who arrive and have an incredible experience, you're more likely to have better uptake than those 100 people who weren't able to fully participate and engage. And we're seeing change. For example, when we spoke to national sport administrators from a national sport organization, they indicated that, in fact, they are picking up our resources, and they're beginning to think about how they're planning programming and how they're using it to influence their decisions. And this is what I was talking about when I sat down with my graduate supervisor that very first day, is knowing that we're making impact and creating possibility for change and optimal physical activity participation for persons with disability. I have the privilege of seeing this research in action on a daily basis. In addition to my responsibilities as a researcher and an educator within the university, I also am the co-director of Kingston Revved Up. Revved Up is an exercise program for 200 community-dwelling adults with intellectual disability and/or physical disability. We also have 20 participants who participate from across Canada and online or our Revved Up at Home programming. We started Revved Up in 2007, a year after I arrived here at Queen's. And this is one of our first members. She's been with us since the beginning, and she comes twice a week to exercise and really to be part and to engage with the Queen's students who are integral to our success. Revved Up is strategically based on our principles of quality participation. We're thoughtful in the activities that we integrate into our programming. For example, Halloween is coming. We'll have an activity where people get to bring their costumes if they prefer. We also encourage our students to ask questions and share experiences with our members. And as a result, the outcomes are incredible. As I said, we have participants who have been with us since the beginning. We also hear stories of improved physical functioning, where people are experiencing autonomy not only in the gym, but also at home. They're able to dress themselves, which they weren't able to do before. They're able to climb stairs, which is allowing them to participate and return to their homes in ways that they couldn't before. Moreover, the thing that our members highlight the most is the role of the students. Indeed, every Revved Up member is paired with a Queen student, either as a volunteer or as an intern in our Certificate of Disability and Physical Activity. And it's the conversation and the bonds that our members form with these students that is unmatched. And recognizing that Revved Up has something magical is part of what motivated my research in quality participation. And it also has allowed us an avenue and a living laboratory, if you would, to explore this concept of quality participation. In collaboration with my colleague, Dr. Jennifer Tomasoni, we've conducted a series of projects to explore what is that magic that Revved Up has. We've compared that to the magic that's offered at other community-based exercise programs across Canada. And using that process that I mentioned to you that involves consensus process and expert opinion, we too have developed an understanding of what quality participation means in community-based exercise programs. We've created, again, a resource that is widely available that identifies, now my colleague Jennifer Tomasoni is one of the most rigorous scholars I know. It has 87 strategies or ways to create quality experience and to contribute to those building blocks. What is incredible is that the same 6 building blocks that I mentioned, autonomy, belongingness, challenge, engagement, mastery, and meaning, hold. They're consistent and they align with the stories that we're hearing from our participants. We're on to something. With these strategies, we're able to encourage our students to think about how each time they come into the gym, they enhance the quality of experience of our members. Moreover, we're able to share this information with the community of practice, of organizations from across Canada that we have formed to share information and to problem solve. Hey, this particular strategy isn't working for me. What can I do? It's allowed us at Queen's to really be leaders in the area of community-based exercise programming for persons with disability. And certainly the impact that this work has had on our members and persons living in Kingston with disability has been incredible. But what kind of is an unexpected impact is the impact it's had on our students. As I mentioned, students are integral in our work. Each term, we train at least 100 students. And when I say each term, I mean fall, winter, and spring, summer. So approximately 300 student volunteers, as well as our 150 student interns. And these students' view of disability truly is transformed. And having a deeper understanding of disability, this means we're training citizens who can enter their communities to create quality experience. It means we're training citizens and potential healthcare professionals, future educators, future entrepreneurs to think about quality experiences for persons with disability. Moreover, this has provided us with an understanding of the critical competencies for training qualified exercise professionals. So again, using that consensus-based process that is foundational to our work, we are now leading the way in creating a competency-based framework for qualified exercise professionals. Next fall, our program will be the first in Canada to implement competency-based training for qualified exercise professionals to support and engage persons with disability. We truly are leading the way. And the other aspect that we see is that not only are we shaping the experiences and the knowledge of our students, but we're transforming their lives. We have students who come in who are homesick and now have the opportunity to connect with one of our members. They decide to stay in the Queen's community because they want to continue to be connected to Rev'd Up. We have students who constantly tell us that they didn't really realize that this was the professional path that they wanted to take. But in fact, because of the opportunity to create quality experiences, to create connection, and actually for them to experience a sense of belonging, challenge, engagement, mastery, meaning, and autonomy, that they are choosing new careers, they're making different decisions, and they're truly enjoying their experience at Queen's. And it's from the stories of our Rev'd Up members and our students at Queen's that I'm convinced that our work is making an impact. Thank you.
Thank you, Amy. We have a little time for questions, if there are any. Why don't yes, we have a question down there.
If there is no other question,
we'll start with you.
Sorry? What did you say?
We'll start with your question.
Hello, thank you so much for the presentation. I just have a question regarding the like the brain and the body and the spirit and the soul, you know, because like a physical and the metaphysical, you can say. So my question is that because you're dealing in that situations, may sound controversial, but have you noticed that any experience or observation that there is something metaphysical, like not related to too much to the brain and not related too much to the body of the people who are have disability, you know?
Sure. So that you're asking if we're noticing experiences or outcomes that might not necessarily be related to cognition or to physical outcomes. And in fact, I actually think that might be what we're capturing. We're capturing and creating opportunities for joy and happiness. We have many members of in our program for whom coming to Rev'd Up is really their social event of the week. And certainly it's that aspect and that element of quality participation and particularly belongingness that I think is particularly critical for some of our members in creating well-being.
Any other questions? Yes, right at the back there.
Yeah, the program looks amazing. Thank you for everything you're doing. Do you know if there's anything similar for children with disabilities?
In Kingston?
Yeah.
There are a few opportunities, and they tend to be sport-related, which makes sense, because if you think of it, we don't usually see kids at the gym. So we have an excellent swim program at the YMCA that is led by Vicki Keith, who is, for those of you who don't know Vicki, who is a marathon swimmer who's broken many a record and has trained Paralympians, but also trained people who just really, athletes who just really like to swim. We also have a really exciting initiative where we have wheelchair basketball that is starting to grow. And it's offered on campus, actually. And we have para-ice hockey as well, or sledge hockey in Kingston. And then there's some other exciting initiatives that are happening. An organization called Kids Inclusive is working with the city of Kingston, who has secured funding and is beginning planning for construction of a new playground for June 2026 is the beginning of the construction. So I think there's some really exciting initiatives that are happening.
Amazing, thank you.
So, yes, question right there. Do we have a...
I'm interested in your program for exercise for people on the autism spectrum, which tends to be, I think, more of an individualistic situation for the person suffering from this. Do you find that exercise is a good way to create, if you like, more of a community involvement for such individuals?
Sure, and we also have many of our members are along the autism spectrum. And that's what's pretty magical about this concept of quality participation, because it actually is quite individual. So we see variation in what's important from one person to the other. So I asked you to think about what might define a quality experience for you. And perhaps you identified one building block, and I identified another. And so as we train our students to understand and explore the needs of the client or member that they'll be working with, they'll begin to understand how to support individuals based on their individual needs. And what we can do from there is we have the one-on-one partnerships, and then there's a number of kind of social events. We have a wonderful talent show at Christmas time, for example, and people can choose to come or not. And we can also adapt and have people come at certain times depending on kind of their sensory needs. So there are a number of opportunities to build social skills and connection as desired and as appropriate for the individual.
All right. Are there any further questions? That really touched exactly on my question, which was, I was just reminded when you presented your 6 building blocks of Richard Bathurst's sort of 6 parameters for looking at sustainability. And I was thinking about, whether you had adjustments by community or by individual.
Certainly, and that is the ideal, is to be able to tailor each of our approaches to our individual members. And we're challenging ourselves through the Canadian Disability Participation Project in particular to begin to really think about individuals who aren't represented in our research and to ensure that we engage and promote quality participation. So one of the initiatives that we have where we'll be launching a new set of resources and ideally working with municipalities to support programming for power chair users, for example, including power chair soccer, power chair hockey, bocce, for example. And again, what we're finding is that the same building blocks resonate. It just may be how you foster them and what's important for one individual versus another.
All right.
Excellent.
Thank you very much, Dr. LATIMER-CHEUNG. Thank you. So our final speaker for today is John SMOL, who is a distinguished university professor in the Department of Biology, cross-appointed with the School of Environmental Studies here at Queen's University, where he also held the Canada Research Chair in Environmental Change for the maximum 3 7-year terms. That was from 2001 to 2021. SMOL founded and co-directs the Paleoecological Environmental Assessment and Research Lab, known as PEARL, for people like me who have trouble pronouncing the words. A group of around 35 students and other scientists dedicated to the study of long-term global environmental change, especially as it relates to lake ecosystems. John has authored more than 750 journal publications and chapters since 1980, as well as having completed 24 books. Much of his research deals with the impacts of climatic change, acidification, eutrophication, contaminant transport, and other environmental stressors. SMOL was the founding editor of the Journal of Paleolimnology from 1987 to 2007, and is currently editor of Environmental Reviews. Since 1990, John has received 7 honorary doctorates and has been awarded more than 100 research and teaching awards and fellowships, including the Enser Kurtzberg Gold Medal as Canada's top scientist or engineer, the Vega Medal from the King of Sweden, and the International Ecology Institute Prize. Amongst his 15 teaching and outreach awards, he was named a 3M Teaching Fellow, and following a nationwide search, Nature chose John as Canada's top mid-career science mentor. He's an elected Fellow of the Royal Society of Canada, the Royal Society in London, and an international member of the U.S. Academy of Sciences. He was elected President of the Academy of Science, Royal Society of Canada, from 2019 to 2022, and in 2013, he was named an Officer of the Order of Canada. John.
Let's see, there it is. I can bring that up here. That would be better. That's doing something. Did that do it?
Restart your slides.
Restart my slides. Oh, it's working. Thank you. Thank you. Shouldn't be so surprised when it works, but well, thank you very much, and thank the organizers and the Royal Society of Canada for this important event, and I think it's gone very nicely. I've been coming to these for some time. I've been a fellow for, I believe, we did some math. I think I'm going into year 31. So we've been doing these for a long time, and I'm really wonderful that they're back after a loss with COVID. The topic I wanted to discuss today referred to as the forgotten lakes. And these are lakes that have been forgotten largely by Western scientists and monitoring programs. And these are lakes that are on Indigenous lands. And so this is some of the more recent work our lab has been doing, which was braiding Indigenous knowledge with lake sediment archives. What we do is we reconstruct environmental history from the mud at the bottom of a lake. It sounds like alchemy or hocus pocus, but I can assure you, as I'm going to try and show you, there's a remarkable history in the mud at the bottom of lakes. Lakes slowly fill over time, and it's like a time machine. I sometimes compare it to like the black box on an airplane, or that we can actually go back in time and reconstruct how the environment has changed, what caused the change. Of course, this can help for evidence-based policy. I'd like to acknowledge immediately that what I'm going to be showing you is not work that I've done personally. A very very dedicated group of graduate students. I named some of them here, as well as some other colleagues that are intimately associated with this issue. We have real problems with time scales in environmental and ecological research. These are some of the important environmental policy questions that we typically ask. We want to know what were pre-disturbance conditions. I cut my teeth on acid rain at this university in my 20s, and the big question in the sort of late 1980s, thereabouts, was, have lakes acidified? Now, you could go to a whole bunch of lakes and you could measure the current acidity and you could show the lakes are acid. But many industries who were causing acid rain were vehemently opposed to these ideas that they caused them because they'd have to be involved in the cleanup. And they would say the lakes are acid, but they've always been acid. They've been acid for 12,000 years. How can you show that these lakes acidified? Sorensen only invented pH in 1909, and certainly no one was measuring the acidity of lakes in Algonquin Park or in Adirondack Park in the 1800s, which is what you'd have to do. You need to know pre-impact conditions. You need to know the range of natural variability. I think climate change is a good example of that. There's no question climate has very seriously been affected by humans, but there is variability in climate change. And to show that we have something very strange happening to climate and that humans are causing it, we need to know long-term records. You need to know natural variability. You want to know, have conditions changed? How much? How fast? When? Why? Each of these has a time or temporal component associated with it, and that's one of the biggest challenges we have in environmental research. I thought I just did this recently, but I see the date 2018. As you get older, things move quickly, I think. But 2018, what I did, I published this in 2019, but I asked the simple question, how long are most aquatic monitoring programs? And went to the International Journal Environmental Monitoring and Assessment. And there were 423 papers published the previous years on aquatics. And as you can see, about 2/3 of the studies were less than 1 year in duration. Actually, over 90% were under 3 years in duration. That's not to say 3 years or less is not enough to make meaningful studies. Of course it is. Most PhD students have 3 years of field work and so on and so forth. But if you think of the questions I posed in the previous slide, it's not long enough to get those answers. And that's the issue of timescales, or as I say, history is important. The past matters. So what do? We try and push that environmental record back in time, and we do that in different ways. One of the ways we do is any historical records. I said we didn't have pH going into the 1800s, but we had some evidence from fishing clubs about fishing declines, for example, or angling declines. We know from climate, maybe from the Hudson's Bay records, they weren't taking the temperature, but they would say like the lake froze. You know, this is from 1700s. The lake froze today or the river thawed today. That sort of embeds some climate information that we can use. There's this, wrong button. Of course, there's this whole spectrum of various types of traditional knowledge, which I'll be speaking about today. There's a whole field of modeling. I won't have time to talk about modeling, and I'm definitely not a modeler. But I'm going to focus on this one around here, natural archives. All around us on the planet is measuring the environment for us and storing that information. We as historical ecologists or whatever, paleolimnologists, which I guess is technically my term, we have to figure out ways to tease apart that information in a reproducible and quantitative manner that's meaningful to other scientists and the public at large. And so there's many ways we can do that. I mean, there's ice cores, there's coral reefs, and so on and so forth. The technique I'm going to be talking about is where there's about 35 people on the 4th floor of the biology building doing it, called paleolimnology. That's a $20 word for working with lake sediments. Paleo is the history, limnology is the study of lakes and rivers. It's like paleooceanography, but on lakes. And the overall process is fairly straightforward. Lakes slowly fill with mud. 24 hours a day, lake sediments are accumulating. In this part of the world, Ontario, the lakes formed about 12,000 years ago, the end of the last ice age. The massive ice age, if you came here about 15,000, 18,000 years ago, there'd be about 3-4 kilometers of ice sitting on this building. We were in the middle of the ice age, or nearing the end of the ice age. The ice pushed all the material forward, gouged out all these basins that form all the lakes in Canada. When the ice finally melted, for reasons we understand, with changes in the sun and so forth, changes in the Earth's wobble, the big ice sheets retreated, and one legacy of that is all the lakes around us. That was point zero when the lake formed. Since then, a history book's been accumulating. Most lakes in Ontario, I would say, have about 3-4 meters of sediment over those 12,000 years. Some have more, some have less, but we work that out. In that sediment is an incredible library of information. And that's what we do. We tease it apart in a quantitative way. And it's because sediments come from a whole variety of sources. They come from material coming from outside the lake, things like pollen grains, aerially transported contaminants, soil, plant fragments, charcoal, and so forth. I'm a limnologist. I'm usually more interested in what's happening in the lake itself, although you can't divorce what happens in the lake from what happens outside. But virtually everything living in that lake is leaving some sort of morphological or biogeochemical marker in the sediments. Not only that, there's also chemical precipitates and so on and so forth, and I'll show you those in the next slide. I'm going to focus here. I'm not going to go back 12,000 years. I'm going to be mainly focusing on the last few hundred years. So there's different techniques to get back 12,000 years of history, or let's say the last 200 or 300 years of history. If you want to get the last 200 or 300 years of history, you only need about 50 centimeters of sediment. And this is what, some of the techniques we developed during acid rain. We needed to get a fine resolution record of the last few hundred years. And so what we did, these were cores developed by John Glue, now deceased. He was in my lab. And they're pretty straightforward. It's actually quite straight. Surface sediments are about the consistency of a milkshake. So you have to be very careful. You don't want to mix the pages around because that's going to be your profile. I use the analogy that it's a bit like if you have a milkshake in front of you and a straw, and you put the straw into the milkshake and you put your thumb on top of the straw and you pull it out. You kind of take a core of your milkshake. That's sort of what we're doing here. This instrument goes down on this rope and it's in the open position. It looks like a plumber's plunger here. It's in the open position. We slowly lower that core into that very wet sediment. Once we're at the depth we want, we send a lead messenger down on this line. It clicks the trigger and it's like, you know, puts your thumb on the straw, if you like. And what you have there is about 200-300 years of lake history. And so then we have to section it. It's very wet. Here I'm sectioning at about 1/2 centimeter. In most lakes, that's about 3 or 4 years of lake history. The deeper I go, the older it gets. It looks like mud, but that mud is full of information. It's full of different types of chemical markers. Things like, I'm going to be talking about mining, metals, all the various metals that are coming out with mining, lead, zinc, whatever, so forth, copper. That is preserved in the sediment profile. Some of them not perfectly, and we understand that, but there's ways we can discuss that. You know, some of it can move in this post-deposition issues, but that's fairly well understood. PCBs, DDT, PAHs, all these things are making their way into that history book at the bottom of a lake. We can reconstruct how the terrestrial vegetation has changed because of pollen. There's this whole field called palynology, the study of pollen grains and spores. Anyone who suffers from hay fever in the audience know there can be a lot of pollen in the air. Different plants produce different types of pollen grains. And sort of an embarrassment to my botanical training, but if you show me a pollen grain, I can tell you what tree it's from. If you show me the tree, I may not be able to tell you what it is. But if you show me the pollen, I'm good. But that pollen grain is very well preserved in lake sediments. And from that, we can reconstruct how the terrestrial vegetation has changed. We can reconstruct when agriculture started, things like that. And there's a whole spectrum of things that lived in the lake that we can reconstruct. If you know what lived in the lake, you can reconstruct the ecology of the ecosystem and how it's changed. This includes a whole variety of algal fossils, especially diatoms. Diatoms is one group of algae. That's all the photosynthesizers in lakes and rivers. Diatoms are extremely common types of algae. There are various estimates, something like 1/4 to 1/3 of the primary production, the photosynthesis on this planet comes from diatoms. If you think about it, since they're photosynthesized, they produce oxygen, so about 1 of every 3 breaths you take is oxygen coming from diatoms. There's thousands of species. Different species live in very different environments. As I'll show you, some live in salty environments, some live in freshwater environments, some live in the middle. We have calibrated these species, and I won't be able to show you how we do that, but we know when you see this, that you have 20% of this and 30% of that, 15% of this, that was about 10 grams per liter salinity. We actually have that calibrated. Or pH. That's what we did in the acid rain days. We had some species that are only found in very acid water, some only in very alkaline, some in the middle. We could calibrate them to their ecological preferences. Of course, the cell walls are glass. Oh, you're not going to choke on these, by the way. You can put hundreds on the head of a pin. This is extremely high microscopy. But their cell walls are glass, so they're perfectly preserved for thousands and thousands of years. And the structure of the cell wall is species-specific. So by looking at, that's an Asterianella formosa, for example, we can tell what the species is. But it's not just the algae. We can look at the animals that lived in the lake, too. Things like Cladoskera. Cladoskera I'll talk a bit about here. Sometimes called water fleas. There are many, many species, but these are often the key indicators of food webs. They're fish food. They're all sorts of things. It's a bit like archaeologists. Unfortunately, the entire Cladosteran doesn't preserve, the entire water flea. It breaks apart its exoskeleton. But it's much like an archaeologist who finds a bone and says, you know, this is the wrist bone of a chimpanzee or something. Expert can look at these different parts and say that's part of a bosmine, a Longiostris, or Chidorus sphericus, and so forth. We also are interested in what's happening in the deep water. And that's usually, now if you want to find out what's in deep water, you have to use organisms that live in the deep water. And that's usually benthic insects. These are the chironomids. Chironomids, those are the ones that are around the lake. You see these clouds. That's the adult stage. But they spend most of their time in the lake in these little larval stages. It's a bit like paleodentistry, where the only thing it preserves is the head capsule, but different species have very different head capsules. And some live, for example, in very low oxygen waters, some live in very high oxygen waters, and so on and so forth. We have a paleo-oxygen meter there. So, you know, you can have a paleo-salinity meter, paleo-pH meter, paleo-oxygen meter, paleo-fish meter. You start putting this together, and you can reconstruct what happened in the lake. So the overall approach is fairly straightforward. We choose our study lake, we take a sediment core, we section and we date it. You know, we have to know where we are in the core. If we're going back thousands of years, we use C14 or radiocarbon, the same thing archaeologists use. But for the last 150 years, the half-lives are wrong, so we have to use something else. Typically we use lead-210. It's a naturally occurring isotope, has a half-life of 22.2 years. We have 4 gamma counters over in our labs there, and by measuring how much lead-210 is there, we can reconstruct. This is about 1940, this is about 1920, this is about 1880, and so on and so forth. Then this is a very long step looking at the indicators. We analyze the data, and we go from there. Now, I wanted to talk here about some recent work we're doing, working very closely with Indigenous groups. Now, I've been working with some Indigenous groups for some time. As some of you may know, a large part of my program has been in the Arctic, where you work with Indigenous groups, I think, more frequently than perhaps what we did in the South. Indigenous groups, of course, you know, I sometimes hear Indigenous this. I mean, it's a very diverse, very complex situation. I mean, in Inuit, we have basically 5 major groups. The First Nations, there's greater than 630, about 50 main Indigenous languages. There's the Métis. So I'm going to take you just in a few examples. I'm going to give you one example with the Inuvialuit, which are up here in the Mackenzie Delta, a quick example there. And then I'm going to take an example from Yukon Territory, and then I'm going to take an example from Ontario. And I'm going to talk about what we're actually trying to do. In paleolimnology, we look backwards for information. We figure that's where a lot of the information lays hidden. That has remarkable similarities to much of traditional knowledge. Much of traditional knowledge is looking backwards. What happened, what our elders said, what our ancestors said, what's in our traditional background. In some ways, they braid together very nicely. And I'm going to give 2 examples. First is the older way we did it, and that's using Indigenous knowledge as peer review, I'd say. We do a study, we decide what we found with Western knowledge, and then we'd ask Indigenous peoples, knowledge holders, this is what, you know, does this match what your knowledge tells us? That's the first example. We've moved on to that in a different way. We're now, from day one, we're co-developing the questions and co-developing how we actually do the research. So first I'll give you a quick example of situation 1. A fairly simple example, but an important one, I think. It made headlines. And we asked the question, we hear a lot about flooding. You hear about flooding like in Florida and North Carolina, sometimes in New York, but flooding can happen in the Arctic too. And This is referring to an unprecedented Arctic freshwater ecosystem changes following a marine storm surge. I'm going to take you up to the Mackenzie Delta, which I think many of you know, but it's up here in mainland Canada. It's an extremely flat, very important, second largest Arctic delta in the world. Very important ecosystem, very flat area. It's going to be key. And there was a storm surge in 1999, a major storm surge. So this happened in September. In September 24th, winds from the northwest came in at 76 kilometers and produced a storm surge. So the winds came, right behind it came ocean water. 2 meters of ocean water went in 20 kilometers, lasted for 2 days. No one was killed, I'll just tell you, but if someone was there, they'd be dead. From hypothermia, if nothing else. You can't, there's so long you can be in freezing cold water, and certainly not for 48 hours. It flooded 20 kilometers inland. And what it did, it left what we call the dead zone. There's the Arctic Ocean in the background. You can see exactly the line, how far it got. It killed everything. Still, over 20 years later, still, everything's dead. You can see exactly how far the line went. This was not hit, this was hit. You see there's also a lot of lakes that were in the area. The question was asked, was this a strange, unprecedented event in 1999? And if so, why would it have happened only in 1990? Why did it not happen earlier? First, we have to determine, was it an unprecedented event? So I'm using a simple example to start. How are we going to do this? Well, with paleo, there's a lot of lakes there. If we core the lakes, we should be able to say when the lake got salty. And did it get salty many times in its past? And there's many ways we did this, but one of them was diatoms. Just like I said, diatoms are very good at reconstructing pH. They're very good at reconstructing salt as well. There's different species that live in freshwater, brackish water, saline waters. And again, we've quantified these to a high degree of certainty. And that shouldn't surprise us. You know, we have saltwater fish, we have freshwater fish, we have brackish water fish. The same for hundreds of species of diatoms. So we have a paleosalinity meter. So what did we do? Well, here's a satellite image. There's what the so-called dead zone is. I think these are quite striking. You can see that's exactly how far the salt water got in 1999. So these lakes are fresh, these lakes are not. So the questions, how common are these storm surges? The impression was it was completely unprecedented. Are they really unprecedented and linked to climate warming? And what were the ecological effects? So we used two different techniques. First, we did paleolimnology. Then we did a peer review with Indigenous knowledge. What did we do? Well, here's another satellite image. You can see the dead zone. These are all in the dead zone here on the left. That's a lake outside the dead zone. We said, let's core all these lakes and see where do we get saltwater diatoms. At what year do we get saltwater diatoms? I'll show you a few slides. I know these slides are terrible to look at, but I've tried to make them as simple as possible. This is the last 300 years. So here's lead-210 dating, brings us down to 1850. If we extrapolate, that's going to the 1600s, 1700s. So that's like a time machine. The deeper you go, the older you get. These are the dates we have. These are the percentage of the main diatom fossils. If they're in red, they're saltwater diatoms. If they're green, they're freshwater diatoms. Where's 1999? There's 1999, which we dated with lead-210. Well, I think you can quite clearly see something remarkable happened in 1999, the storm surge. The lakes are still salty. They're still salty diatoms. It never happened over the last 300 years. Yeah, there's little hints here and there of tiny, tiny marine events, but nothing like 30, 40% salt diatoms. It was an unprecedented event based on this. So we're paleoecologists, we'll go back 300 years. Let's go back to the lake started. So we take a long core. We take a much longer core. Same thing, red is salt, green is not salt, green is fresh. This goes back to this lake formed over 1,000 years ago. The only place we see any significant saltwater diatoms are 1999. Now there's other changes. Your eyes may well be going here, and we know what that is. Those are river diatoms. That's when that lake it's part of the Mackenzie River system. We can understand that, but they're fresh water. The thing that's clear here, the only time we got saline conditions is 1999 and after that. That was one lake. We did it on many lakes. There's the dead zone. I'm not going to go into any detail. I think it's pretty clear. Every single lake on the landscape is always post-1999. We had one control lake outside the dead zone, no salt diatoms. It's clear from the paleo data, it's unprecedented in this lake's history, the 1990s storm surge. So where do we bring our traditional knowledge holders? Well, this was done again with Steve Coquel as the lead, who lives up in Yellowknife. We got together, and they got together a workshop with Indigenous knowledge holders who live in the overall area. And they did this jointly with the Inuvialuit Joint Secretary. It was a 2-day workshop. It was organized. And they asked the hunters and trapper associations of the 3 communities that live nearby. Thankfully, no one was killed. But they did use this area, the area for hunting and moving around. And a total of 9 hunters were selected as knowledge holders who knew the land well. And to avoid bias, we didn't show them what we found. We did like a peer review, I guess. We said, can you tell us what was unprecedented? Was it unprecedented storm surge? What does your traditional knowledge say about past flooding? The traditional knowledge holders identified, just like our data, 1999 was unprecedented. And it's interesting how they used even how, it's hard, I mean, I can't remember dates at all, but they would say, oh yeah, Johnny was 2 years old, so that was 1999. They used like children's ages or events in their lives, but they clearly identified 99 storm surge. They also identified smaller, earlier storm surge, and those match our little bumps. We had a few other little bumps along the way. They actually matched quite nicely. And they discussed the die-off, we call it the dead zone because all the vegetation's dead. They said, sure enough, that's correct. That was an immediate one. And they'd never seen that type of dead vegetation. So that matched what we had. But then they told us a whole lot of other stuff that there's no way diatoms would have told you. So we learned a whole lot of stuff from this. They said that there were, between the die-off and the willows and grasses, there was much change in the local ecosystem. For example, moose were common. They used to go moose hunting there. The moose are now gone, they said. I mean, we can add a list here. Other information didn't capture. They used to go there for waterfowl hunting, especially geese. There are hardly any now, so they don't use it as hunting anymore. And they now seek different places to get their geese and their eggs and so forth. So there's a lot of stuff they told us. Now this, I think, we might not think of the Arctic as a place where you get storm surges, but there's something like, I think, 48 or so Inuit communities, all but one's on the ocean. You may ask, okay, why did it happen? And again, the usual suspects seem to explain this. One, climate warming. We're getting bigger storms, more intense storms, more of these so-called episodic events. 2, with climate warming, you get higher water levels. Again, more susceptible to storm surges. But here's the big one. If the same storm had happened 50 years ago, there would be no storm surge. Sea ice is disappearing, and the big storms come in late September, early October. 50 years ago, the sea ice was still there. If you put sea ice, you think of as a blanket, and you put a whole lot of wind blowing, you're not going to get a storm surge. You've got like a blanket on the ocean. Now the sea ice is gone, and so you've lost that guarantee against these storm surges. A few years ago, another storm surge happened. So it's coming, a second one has now happened, and we're back there now studying it. That was a peer review kind of study. I'm going to just finish with 2 examples that's Indigenous-led, Indigenous co-led, I should say. And at the overall question, this has a lot to do, I believe, with reconciliation and other issues such as that, but what were the states of lakes on Indigenous lands before settlers arrived? And how have they changed since then? And I'm going to look very quickly at the impact of silver mining in Yukon, and then I'm going to go to Sudbury for the forgotten lakes in Sudbury. So forgotten lakes in Yukon, forgotten lakes in Sudbury, and take a look at how they've changed due to settlers' impacts. First, take you up to Yukon. Now we think of the Yukon, the gold rush, and we are looking at the effects of the gold rush, by the way, 1896 to about 1900. But there was a second rush called the Silver Rush. I'm going to take you to the Keno City Silver District here. Second largest silver producer in that time in North America, 4th largest globally. A lot of silver was retrieved from this part of Yukon. The issue was that the gold rush, or the silver rush, was based on traditional grounds. And this was the Natchoiniak First Nation, and they are very concerned. They want to know, dealing now, okay, so what were these lakes before? We know what the lakes are like now. What were the lakes like before the mines were open, before they were digging up all this silver? How did mining affect nearby lakes? And has there been any recovery since the mining is more or less gone in most areas? I'll show you a quick example of one lake. I was right at the mine, Crystal Lake. And I won't show you much because, not surprisingly, this lake, that's right, where all the ore is back here, the silver mine. We even find tailings right in this small lake. We did this as a demonstration project. And usually when we work with Indigenous groups, we talk, we consult, then we do a demonstration project, just show you what we can do, and are you interested in continuing this? We thought, well, let's start on the bullseye, ground zero. We have all sorts of data, but I'm just going to show you the metals. And we did find some very interesting. These are some of the major metals they're worried about: arsenic, cadmium, chromium, copper, lead, zinc. We did find some okay, so this is going back in time. So this is going back to about the 1700s here. What's interesting is before the mine was there, even before the mine was there, metal concentrations were already high. This is not surprising. That's why they went mining there, because the metals that they mined were very high in this part of Yukon. And so this is important for background conditions. You have to know what are realistic targets. Okay, that's not to say the mining had no effect. Look at arsenic, one that they're really worried about, cadmium, all these greatly increased during the time of mining. And then we saw some modest recovery in most of these elements when the mine started closing down. Okay, this was not surprising. And, they said, yeah, background conditions were high. Some recovery is evident near the surface. And even, the Indigenous group says, yep, okay, well, we knew that lake was a goner. I mean, we can see the tailings in there. We've lost that one, let's say. We want to know what our fishing lakes are like, so that's where we're going into now. What about the lakes that are about 10 kilometers away from the mine? That's where we go fishing now. We don't go to these lakes. But there was dust everywhere. Did the dust affect lakes that are farther away? So are there signs of long-range pollution, such as the Hansen Lakes, which are up here? They're fishing lakes. Here's point 0, where I just showed you the big mess. They're about 10 kilometers away. They ask, are there big changes? Do we have something to worry about in our fishing lakes? I'll just show you the metals. We showed a lot of other things. I'll show you a little more in the next example. Background, just like at Keno City, the background metals were high. And this is, again, what we're finding in many of these mining areas, but that's why they went mining there, because the background metals were high. However, there's a slight increase the time of mining, but very minor compared to Crystal Lake. I think this is easier to see. I'm trying to find out easier ways to say it. Crystal is the lake that's the bullseye, right, where the mine is. Hansen Lake is one of their fishing lakes. These are the different metals in the concentration. See, there's no comparison between the two. It's really a major change. So similar to Crystal Lake, background or pre-mining metal concentrations were elevated, but to a much lower degree. Although some mining dust went into, affected the fishing lakes, a good news story, comparatively minor. There were massive changes linked to climate change, which I won't have time to go into here, but that's a whole separate story. It's not to say there's no changes in the lakes, but it appears their fishing lakes are more or less separated from the effect of the mine. So that's a good news story. I'll just conclude with one last example. I'm going to take you close to home near Sudbury, where I've done a tremendous amount of work, but not on Indigenous lands, the Forgotten Lakes. I did some of my very earliest work in the 1980s. And I'm going to take you to the AAFN First Nation, which is near Sudbury. So there's where the AFN territory is. And they're part of the Robinson-Huron Treaty of 1850 that was signed by AFN and settlers. The treaty says we're going to share the land, and AFN members get an annual payment for sharing the land of $4. That's what they agreed to in the 1800s. Today, they get $4 a year. That's being challenged in the courts right now, but we might help them along here. it really resonated when we were at one, and then you have long consultations before you start doing this work, but consultation from an elder who asked this question: can you tell us what our lakes were like when our ancestors signed the Robinson Treaty of 1850? And we said, yeah, I think that's what we can do. So that's what I'm going to show you. And this was, again, very much co-developing questions. They want to know very clearly what were these lakes like at the signing of the treaty, or right before the signing of the Treaty of 1850. Have the lakes been affected by Sudbury acid and metal deposition? And given the marked declines in emissions since the 1970s, has there been any improvement in these lakes, if in fact they were affected, because we don't have long-term monitoring data? And to what extent are other stressors like accelerated climate warming affecting these lakes? So Sudbury, as you probably know, major mining area, and mining started a long time ago. Sudbury was polluting the environment in the 1880s. They had these open roasting beds. Massive amounts of acid were coming out of these roasting. They just basically baked ore out in these roasting beds with logs, fumigated the whole area. All the trees died, where you can see what was happening. That's all been happening since the 1880s. Sudbury's also the sort of poster site for recovery in many ways. Not total recovery, but with strong legislation in the 1970s and continuing on. This is what Sudbury was pumping out in the 1960s when they started measuring it. This is what Sudbury's pumping now, and the superstack is gone and everything. So it's seen as a big example of what happened. By the 1970s, it was peak production. So we're now on the AFN land. We're going to look at Lake 10. It's 22.8 kilometers from the Copper Cliff Vale Conference. I'm showing you this lake because this is a lake they're sort of forgotten. This one had one datum point from the 1970s. Dick Beamish was doing a fish survey of the Sudbury area in the 1970s, and went on First Nations land and took a sample from one lake, Lake 10. And what they found, in 1974, the lake had a remarkably low pH of 4.5, very low calcium, and very high metals. When we go back, pH has gone up significantly, 5.82. Calcium's still extremely low, and metals are much lower. But we want to see what this was like when they signed the treaty and what happened since then. We look at metals, they're a major stressor. Here are the major metals that we worry about. These are the ages, so we're going down to somewhere in the late 1600s, early 1700s. There's the treaty. First question, well, no, your lakes are different. I don't know how else to put it. No, they're not like they were in the pre-1850s. Massive changes in metal concentrations. Now, they are tracking the recovery, not back to background. We haven't gone to background yet. They are tracking a recovery pattern, but massive increases in metals. And there's still, as you can see, arsenic is higher, cadmium is still much higher, mercury is still much higher, and so on and so forth since that time. So the stressors are there. Did these lakes acidify? Well, we kind of hint they acidify because Beamish got that one pH reading in the 1970s. But to find out if they acidify, we look at algal fossils. So let's just see what the algal fossils say. Look at these are chrysophytes. This is a group I described in my master's thesis, still used extensively for acid rain work. These are scaled chrysophytes. Different species have very different pH optimum. Okay, let's put in 1850. Well, in the 1850s, this was a clearly natural ecosystem, very typical of boreal ecosystems, clean, pH probably circumneutral in the high 6s, approaching 7. This is what you find in pristine lakes in Canada now. 1850 treaty, so we look, 1880 is the line when they started doing Sudbury. I think you can see first the massive change with that acidification, then once they brought in the controls, a little less acidification, still massively different from what it was here, but we clearly have a shift to acidic species. We clearly show acidification. We show a slight recovery, just like we know from those two datum points, but clearly this lake is very different than it was pre-1850. Most people don't care about algae. I care about algae because I work on them. What about as you go up the food chain? As I said, we can track almost everything now in lake sediments. What about fish food or the invertebrates, the water fleas? These are critical for ecosystem structure. Let's put in 1850. That's when the treaty was signed. This is a classic, typical, healthy lake ecosystem, full of bosmina, daphnia, a good spectrum of benthic species. We can also do DOC, dissolved organic carbon was high, chlorophyll A was good. Everything looks perfectly normal. What happens? They hung on up until peak acid rain, 1950s, 1940s, 1950s, and a complete shift. We've lost the plankton. We've almost totally lost the invertebrates that live in the open water. The only thing left is what lives in the shallow waters, and even that, as you look at concentration, it's much smaller there. You see this tremendous change has happened, and we see absolutely no recovery. So even though metals have gone down, even though pH has recovered somewhat, not totally, we still see absolutely no recovery in the zoology. That may be due to calcium, because calcium is like, once you lose the calcium, it's very hard to get it back, and these organisms need calcium. It may be due to fisheries, and maybe due to different types of predation, but we're working on that now. We can reconstruct when the fish, there is a question even with the indigenous groups, I think, did this lake have fish? So I heard one say possibly they thought there was, one I'm not sure. We can reconstruct if there were fish, and if so, when the fish died. We're doing that right now. We use these Chiabris, and we can actually answer that question as well. So, wilderness lake, aerial deposition of acid, massive changes to the food web. Everything has changed dramatically. There's some signs of recovery, but not biological recovery. There's chemical recovery, but not biological recovery. So I'm just going to end with 2-3 slides, say what lessons have I learned having been doing this for a while. I'm talking about the co-developed programs. Number one, trust is an issue. Projects need a lot of lead time to develop relationships and mutual respect. Mutual respect is critical. And I'm talking probably, before you start a project, plan a year of consultations. So there's funding involved in this, of travel and so forth. But you have to build that. Trust is in small supply. Everything will take much longer than you may like or expect. I'm a guy who likes to move fairly quickly. You learn patience, and that's important. Everything will take quite a bit longer. Do not arrive with a fully running program and say, okay, this is what we're going to do. What do you want? What do you want to know? Or what do you want to do? Those questions, that whole process has to be co-developed to be a success. Again, co-develop questions, not just your priorities, but really the priorities of the local peoples, and really appreciate that everyone can bring something to the table. You're not there to dictate, but you're there to learn, and I'm very much a learner in this process and still very new at it. Appreciate that funding may be needed, not just for which we normally think of, but funding for honoraria, for salaries, for using their facilities, has a funding component to as well. The data from local knowledge holders needs to be treated and acknowledged properly. Think of it as a colleague's unpublished data, and make sure you have clear permission to use it before you use it. And finally, Indigenous knowledge holders co-author publications. I think this is key. If it's joint information going into a paper, they should also be authors if they'd like to be authors. And when you talk to the Indigenous knowledge holders, they are very excited about that. They still feel very strongly Western science has not accepted Indigenous knowledge as a major contributor to the understanding of environmental issues. And by being co-publishing on manuscripts, that is a major stamp of credibility in their world. And so I think we're at Queen's, and I think we know Senator Murray, our former chancellor, was very intimately associated with the Truth and Reconciliation Commission. I think these are ways we can actually, scientists can contribute to this process, contribute in solid ways that are of considerable interest to the indigenous people that are depending on these types of data. And sometimes people ask me, are these papers going to be published in Nature and Science and things like that? No, probably not. I have enough of those. I think at this stage of my career, I think this is the most important thing I could probably be doing. And so we both look backwards using different methods, but I think there's a lot of synergies between these two. We tend to think of monitoring and paleoecology. Both of them sort of peter out, but they can really have a lot of a lot of interactions between them. And of course, I'd like to thank NSERC for funding this. No mining company would ever fund anything I do. Thank you very much.
So thank you very much, John. We have time for some questions. Yes.
You mentioned that chemical recovery starts
yeah.
At a certain point. Does it follow that biological recovery will automatically come after that?
Yeah, it depends on what. For some of the algae, there's better recovery, but the ecosystem is different. First of all, climate change has happened in them. We have multiple stressors. I didn't want to get into that, but climate has changed. So that we think some of that is simply climate. There are very different types of lakes unrelated to the mining. But the mining and the acidification caused significant other types of changes that are very hard to come back to. One of them, which we published in Science some years ago, 2008, calcium decline. It was sort of an unknown sort of legacy of acid rain. And to put it very quickly, acid rain, there's some areas like Canadian Shield Lakes had very little calcium anyway. We all need calcium. We all know about osteoporosis. Everyone needs calcium. Algae need calcium. Cladocia need calcium. Fish, everything needs calcium. These lakes always had very low calcium, but for thousands of years, that calcium was slowly coming in from the land into the lake, and there was enough of it. It just was in equilibrium. With acid rain, for a short period of time, the calcium in the catchment flushed out into the lake. It's much like if you think of people have like Tums for antacid. That's basically limestone, I guess, that you're eating. And if you put vinegar on it, it's going to fizzle, right? And the same thing happened. What little pockets of calcium were in these Canadian Shield Lakes, they flushed out very quickly. For a little while, there was a lot of calcium, but then the source disappeared. Also, cutting down trees didn't help. Trees have, we're exporting calcium. The wood in this building is calcium from somewhere that was exported here. They ran out of calcium. And so some of these species need calcium, and the calcium's gone, and it's very hard to get it back. So some, like Cladocia, Shelley sitting next to you is an expert on some of these, but some like Cladocia, they can't come back if the calcium's not there. And it's very hard to get it back. So they may never come back. Now, they'll be replaced by other things, but things we don't normally want, like holopedium, again, things like that. So we have made barriers to some of this recovery, not least of which the lake itself has changed with climate change and other things. But we're seeing we see chemical recovery, pH recovery, no problem. We're seeing that, finally. Other things, it's slower, and some maybe never. It's very hard to fix these things after the fact, yeah. Art?
Yes, Professor McDonald.
With great talk, John.
Thank you.
With traditional knowledge, how many generations can you go back with any degree of reliability?
Yeah. It's a sensitive issue, and one I'm sensitive to answer. My view is we're all Homo sapiens and have the same type of brains, same type of memory. I think it's true that if you're in a culture that is intimately associated with the environment, someone living in that environment and talking to their parents and grandparents and so forth will go farther. But it will, in my view, peter out. And so, 1800s, also indigenous groups moved around, obviously, So it does, that's why I had, even on my diagram, I had it sort of petering out. So, and again, there will be very different views on that. But I think if as a biologist speaking, I think there's a certain point where, we might just have the paleo at a certain point. But it goes back far, I would say go farther than my environmental memory. I grew up urban, it's a very different world. If your entire world is that, where you go fishing and how you go fishing and who caught fish, and it really is, there's a fair amount of information, unfortunately not written down. So it is primarily oral tradition, yeah.
John, have you seen any effects of leaded gasoline on lakes?
Yeah.
And is there any recovery?
It's one of our 3 success stories. Not too many success stories in this business. Acid rain, sort of a success story. Ozone depletion, sort of a success story. CFCs. Lead is my third. We didn't have much time to show. Now, if mining is releasing lead, you don't see it. We can even use it as a dating technique. You can see lead increasing in the 1800s, especially that's coming from coal primarily. You can see lead at fuel, the big peak. The removal of lead, we see a very nice recovery happening, and we actually use that as another dating tool. We do, if we have like problems with dating, it says let's do regular lead, not the radioactive lead or whatever. Let's do stable lead, and we see a very typical pattern in not affected by mining, a typical pattern increasing in the 1850s. That's mainly with coal, the peak, and the legislation against leaded gas. So we definitely see that. Yeah. I have 3 happy stories in the environment. That's it. There might be more.
All right. We've sort of reached the end of our official time, and I want to be considerate of our hosts at the Isabel. So please join me in thanking John.
Oh, I can thank you. Do you want me to thank him? Oh, I assumed. I thought that one of you was going to do the thank you. Anyway, thank you. Thank you. First of all, thank you everyone for coming. Thank you very much. We'd like to thank the Queen's University Vice Principal Research Portfolio, the Royal Society of Canada, the Isabel Bader Centre and staff, and certainly thank all the speakers. And, thank you everyone for coming, and we hope to see you next year. Thank you all.